Hello everyone, today I will bring you the third section of RISC-V CH32V208 Bluetooth Low Energy Quick Start, Central Role and Packet Analysis. This section contains the following three parts: Central Role Initialization, Development and Debugging, and Communication Packet Analysis. Let's talk about part 1 first, Central Role Initialization. Let's take a look at the process of the central sending a connection request. The peripheral advertises on channels 37, 38, and 39 in turn. After the central scans the advertisement of the target peripheral on channel 38, it immediately sends a connection request, and the peripheral stops advertising after receiving the connection request. The connection request initiated by the central includes transmit window size, transmit window offset, interval, latency, timeout, channel map, and other information. After receiving the connection request, the peripheral can know when to open the transmit window and the size of the window. During the transmit window, the central will send the first packet to the peripheral. The central's first packet can extend beyond transmit window. If a packet is not received in a transmit window, the peripheral should attempt to receive a packet in a subsequent transmit window. A subsequent transmit window should start connection interval after the start of the previous transmit window with the same transmit window size. After receiving it, the peripheral will reply a dead packet to the central. Once the central receives the reply packet from the peripheral, the connection is established. The first packet received by the peripheral sent by the central determines the anchor point for the first connection event, and therefore the timings of all future connection events in this connection. Subsequent connection event anchors should be connection interval after the previous connection event anchor. Let's take a look at the process of updating parameters between the central and the peripheral in the connected state. The LL connection update indication PDU is a command that can only be initiated by the central. It contains window size, window offset, interval, latency, timeout, and instant. The instant field should be used to indicate the connection event count when the updated parameters should be applied. This is known as the instant. The peripheral should listen to the connection event when connection event count equals instant. The central should allow a minimum of 6 connection events that the peripheral will be listening for before the instant occurs. The connection parameter used before the instant is old. The connection parameter contained in the LL connection update indication PDU and used as the instant and after is new. The central's first packet may extend beyond the transmit window. The first packet sent after the instant by the central determines the new anchor point for the connection events, and therefore timings of all future connection events in this connection. The remaining connection parameters have been mentioned in the previous section, peripheral initialization. Review it if necessary. Then talk about part 2, development and debugging. Let's look at the code. Copy a new project first. Replace the app folder and profile folder with the file content in the central routine. A central project is ready. There is a place to modify on the project properties. Add a 32 kHz clock source selection related macro definition here. The template project uses RSI by default. However, the central communication has higher requirements on the clock, so RSE should be used as a clock source of TMOS. Compare it. No errors. Let's look at the main function. What was said in the previous section will not go into detail. This function is the initialization of the delay function. This function is the initialization of the serial port function. The default initialization is 0.1 to print debugging information. This function is the initialization of the BLE protocol stack. The initialization of the central BLE protocol stack is almost the same as that of the peripheral. Only here is because the clock source of TMOS is changed to LSE. The clock accuracy is initialized to 50 ppm, and there is no need to register the internal 32 kHz calibration function. This function is the initialization of the hardware. Because of the change of the 32 kHz clock source, the clock calibration event here doesn't execute an internal 32 kHz calibration function. This is the initialization function of the GAP central row task, completed by the protocol stack. Just call it. This function initializes some central row parameters. First, look at which events are registered. These events are all related to the role of the central. The first is a mandatory system message event. The second is the central start event. The third is a connection request timeout event. The fourth is the event of service discovery. The fifth is the event of connection parameter update. The sixth is the event of communication speed update. The seventh is the event of writing and reading peripheral characteristics. The eighth is the event that enables notification from the peripheral. The ninth is the event to get the signal strength. The detailed event function will be discussed later when this event is called. Let's take a look at which parameters are initialized. This is to set the scan time. The minimum unit is 625 microseconds. The routine is set to 2400, which is 1.5 seconds. This is to set the minimum connection interval and maximum connection interval after the central and the peripheral are connected. The unit is 1.25 milliseconds. The minimum connection interval time and the maximum connection interval time set by the routine are 25 milliseconds and 125 milliseconds respectively. This is to set the timeout period used for connection judgment disconnection. The unit is 10 milliseconds. The routine is set to 1 second. The parameters related to pairing and bounding are set here. This is to set the pairing passcode. If the passcode is sent from the peripheral to the central, the passcode needs to be entered to pair successfully. This is to set the pairing mode. The default setting is to wait for the peripheral to initiate a pairing request. You can also choose not to allow pairing or initiate a pairing request by the central. This is to set whether to enable the function of preventing man-in-the-middle attacks. Preventing man-in-the-middle attacks is a security feature that prevents the key from being obtained by a third device during the pairing process. This is to set the input and output capability of the peripheral, that is, the way to input or output the passcode. The routine is set without any input and output capabilities. This is to set whether to enable bounding. After enabling it, the central will save the pairing information to the flash, and the peripheral doesn't need to repair when it connects next time. This function is used to initialize the JTT client. This function is to register the task ID of receiving notification data and the indication data of the peripheral. After the registration is completed, when the central receives notification data or indication data, it will report the data to the message event under the task ID. The above is all the initialization of the central. All the functions of the central must be more than that. There are also some functions that are not used or just use the default value, so they are not mentioned. We will talk about it later when it is used in other routines. The next step is to set the central start event, which will be executed immediately after the TMOS starts running, back to the main function. Next, the while loop is executed, and the TMOS starts to run. Now, a total of 2 tasks are initialized in TMOS. One is the task here, which will only periodically call the RF calibration event. The other is the task of the central. The central start event is set. Let's take a look at the central start event. The function called by this event passes 3 parameters to the protocol stack. The first is the ID of the task that receives the message. The second is bounding-related callbacks. One is the callback function for the pairing passcode. This callback function will be called during the pairing process. This function can modify the passcode used for pairing. If not registered, use the default passcode 6 zeros. The other is the callback function of the bounding state. It is used to tell the application layer which pairing state it is currently in. The state include pairing start, pairing completion, bounding completion, and bounding back connection. The third is a callback related to the central row. One is the callback to get the RSSI value. Generally, the application layer calls a function to obtain the RSSI value once. After the controller is obtained, it is reported to the application layer through this callback function. One is the callback of the central state. This state is central initialization completed. This state is that the central has scanned the advertisement data of the peripheral. This state is the end of a scan cycle of the central. This state is the establishment of a connection between the central and the peripheral. This state is the disconnection between the central and the peripheral. This state is the connection parameter update between the central and the peripheral. This state is the communication speed update between the central and the peripheral. This state is that the extended advertisement data has been scanned. This state is that direct advertisement data has been scanned. One is the M2 update callback. This callback is called when the M2 of the communication between the central and the peripheral changes. Next, we download the program to the development board of CH32V208. Through the information printed by the serial port, we can see the running process of the central. We need to prepare 2 CH32V208 development board. One board is used to download the peripheral firmware. After we have determined a peripheral to be connected, we need to change the MAC address of the peripheral to be connected in the routine of the central to that of the peripheral we have prepared. After the modification is complete, download the central firmware to another board. The first line prints the time the firmware was generated. The second line prints the version number of the BLE library. Then start running the TMOS system. After performing the central function initialization, the central starts to scan the peripherals. This is the information printed by the central state change callback function called by the protocol stack. A scanning process will last for 1.5 seconds. Every time the advertisement data of a peripheral is scanned within 1.5 seconds, the central will call the callback function to notify the application layer of the scanned device information. Let's take a look at the code where the bulk printing is executed. First of all, after the central initialization is completed, it will enter the state of initialization completion. The stack will call this state change callback. After entering this branch, executes the function that the central starts to scan. This function has 3 formal parameters. The first parameter is the scan mode. The routine selects a scan that doesn't filter any advertising data. The second parameter is scan enable. The third parameter is whether to enable the whitelist. Whitelist is a filtering mechanism, and users can add devices to the whitelist. If the whitelist is enabled for scanning, the application layer will be notified of the scanning device only when the device in the whitelist is scanned. After this function is executed, the central starts scanning advertisement data. Once the advertisement data is scanned, the protocol stack will call this callback function. The function enters the branch that scans device. This is a custom function. The formal parameters are the scan device address and address type. This function saves the address type, and address type of all scanned devices into the buffer. The buffer space has a certain upper limit. A total of only the device information of the first 80 different peripherals scanned is saved. Here is to save the device information. Here is to print out the device information. After scanning for 1.5 seconds, the scanning ends. The central enters the scan complete state. Then compare whether the MAC address of the scan device matches the address of the peripheral to be connected. If not, restart the scan. If the MAC address of the peripheral to be connected is scanned, the connection request is initiated. The connection is complete here. This part is executed by the code here. After scanning, the protocol stack calls the state change callback function. Go to the branch where the scan is done. Compare the MAC address of the peripheral we are going to connect with the MAC address of the scanned peripheral. If the same MAC address is compared, the loop is exited. If the two values are the same, it means that the device with the same MAC address is found, and the scan starts again. Otherwise, a device with the same MAC address has been scanned. Call this function to initiate a connection request. There are 4 parameters in total. The first parameter is whether to use high duty cycle scanning. The second parameter is whether to use whitelist scanning. The third parameter is the address type of the peripheral to be connected. The fourth parameter is the address of the peripheral to be connected. A connection timeout event is also scheduled here. If the connection is not successful after 2 seconds, stop sending the connection request. If within 2 seconds, the connection between the central and the peripheral is established, the central enters a state where the connection is complete. The protocol stack calls the callback function of the state change and enters this branch. First, stop the connection timeout event. The completion of the connection establishment doesn't mean that the connection establishment is successful. If the connection is established successfully, update the connection status and save the connection handle. Then 4 events are started regularly. The first is an event that discovers peripheral services. Start after timing 1 second. The second is an event of connection parameter update. Start after timing 2 seconds. The third is an event of communication rate update. Start after timing 1.5 seconds. The fourth is an event of periodically obtaining RSSI. Start after timing 1.5 seconds. The third event is not actually started regularly because the judgment condition is false. The details of the event will be discussed later. If the connection establishment fails, the scan is restarted. Look at the serial port printing information. In the second line, after central and peripheral are connected, the protocol stack reports the MTU size as 23. This is no negotiation of the MTU size here, because the default size of the MTU after the central and the peripheral are initialized is 23, which is the minimum value. In the third line, the central obtains the handle range of the custom service in the peripheral, which is OX21 to OXFFFF. On the fourth line, The central gets the handle assigned by the value attribute of characteristic 1 in the custom service, which is OX23. On the 6th line, the central gets the handle assigned by the client characteristic configuration attribute in the custom service, which is OX2D. After obtaining the required handle value, the central writes OX5A to characteristic 1. This is followed by connection parameter updates. Then the central writes OX0001 to the client characteristic configuration attribute to enable peripheral notification. After enabling successfully, the peripheral can notify the central of data. Then the central reads the data of characteristic 1. What is read is the written OX5A. Let's look at the relevant code. First, look at the events that are started regularly. The service discovery event will be explained at the end. This is the connection parameter update event. The update content is that the connection interval update range is 25 milliseconds to 125 milliseconds. The latency is 0, and timeout is 6 seconds. This event is similar to the one mentioned in the peripheral routine, but the command initiated by this function is mandatory and cannot be rejected. The event starts after timing 2 seconds. This is the communication speed update event. The central requests to update the communication speed to 2 Mbps. This is an event that periodically gets RSSI. Get it every 1.5 seconds. Start after timing 1.5 seconds. Next, let's look at the peripheral service discovery event. The purpose of the service discovery is to obtain the handle value assigned by the peripheral to each attribute in the service. Only when the handle is null, the central can operate on the attribute corresponding to the handle. Here the central passes the connection handle, the UID OXFFEO of the non-peripheral service, the size of the UID, and the central task ID to this function. The protocol stack will initiate a find by type value request to the peripheral. After the peripheral response, the protocol stack will report the response information to the message event of the application layer. As for the peripheral's response to other requests or notifications and indications, the protocol stack also reports through message events. This function is used to process the data of the service discovery response. What was just initiated is the request to discover the custom service of the peripheral. So enter this branch. The peripheral returns the handle scope of this custom service. Range is OX21 to OXFFFF. After the scope of the custom service is obtained, prepare to obtain the handle of the attribute whose UID is OXFFE1. You need to pass the connection handle, the range of handles to look for, the UID of the attribute, the size of the UID, and the task ID to this function. The handle scope is the handle scope of the custom service just acquired. The protocol stack will initiate a read by type request to the peripheral. After the peripheral answers, enter this branch. Obtain the handle of characteristic 1 in the peripheral's custom service, which is OX23. Here, the event of writing and reading characteristic 1 is started after timing 1 second. Then continue to get the handle of the attribute whose UID is OX2902. This is the client characteristic configuration attribute. The same function as the previous one is used. You need to pass the connection handle, the range of the handles to look for, the UID of the attribute, the size of the UID, and the task ID to this function. The central then initiates a read by type request to the peripheral. After the peripheral answers, gets handled to the client characteristic configuration attribute in the custom service, which is OX2D. Here, the event that enables the peripheral notification is started after timing 1 second. Let's look at the event of writing and reading characteristic 1. First, determine whether there is ongoing communication, and if not, execute the write operation. Then initialize the write request structure, including the attribute handle, the length of the written data, the value of the written data, and 2 flags. Don't worry about these 2 flags. The protocol stack handles them by itself. Here, the handle OX23 of the value of characteristic 1 is assigned to the handle. The length of the written data is 1 byte. Apply for dynamic memory to store the data to be sent. Assign OX5A to the data to be sent. Then call the write characteristic value function. After sending successfully, wait for the peripheral to reply, and perform the read operation after timing 1 second. The protocol stack reports the response of the peripheral to the application layer through the message event. This part is the written response. Print write is successful, then clear the communication state. Before executing the operation of reading the value of characteristic 1, the timing time of the event that enables the notification of the peripheral is up. This is also a write request, but with different attributes and values. The attribute handle written here is OX2D, and 2 bytes are written. Writing OX0001 is to enable peripheral notification. Writing OX0000 is to disable peripheral notification. After receiving the write response from the peripheral, it means that the enable notification is successful. Then the central receives the data notified by the peripheral. Report notification data to the application layer at this location. Next, the operation of reading the value of characteristic 1 is performed. First, initialize a read request structure, which only contains a variable of the attribute handle. The handle OX23 of the value of characteristic 1 is assigned to the attribute handle. Then call the function to read the characteristic value. Wait for peripheral to respond. Report the read data to the application layer at this location. Print the read data. Then look at the disconnected print. Turn off the power of the peripheral first. After the timeout period is reached and the communication is not successful, the central determines that the connection is disconnected. The disconnect reason code is OX08, which means the communication timed out. Then restart the scan. What is executed is the code here. Clear the central state and handle values first. Then stop getting RSSI event. Print the reason for disconnection. Finally, restart the scan. The above is the full function of the central routine. Through the explanation of the central and the peripheral routines, you should be able to have a certain understanding of the BLE development on the CH32V208. Then talk about PART3, Communication Packet Analysis. During the BLE development process, you can see the running logic of the code by printing the debugging information through the serial port, but you cannot clearly understand the data packets sent by the BLE physical layer. A BLE Analyzer can capture real-time BLE data packets in the air, which can help developers to identify and solve problems. Let's take a look at the packet interaction that occurs during the central and peripheral communication. This is the connectable undirected advertisement packet sent by the peripheral. The packet in the box here is the content of the link layer packet format. The host computer software has made a trade-off for the displayed content, only keeping important data. The link layer packet format includes preamble, access address, PDU, CRC, and optional constant tongue extension. Preamble is used in the receiver to perform frequency synchronization, symbol timing estimation, and automatic gain control training. The preamble is a fixed sequence of alternating 0 and 1 bytes. For packets transmitted on the LE 1 MB, the preamble is 8 bits. For packets transmitted on the LE 2 MB, the preamble is 16 bits. Except the data packets of individual advertising channels, the access address of all other advertising physical channel data packets is OX8889BED6. In the data physical channel, the access address is generated by the link layer of the initiator and included in the connect request sent to the peripheral. The PDU is the advertising channel PDU. The CRC is calculated based on the PDU. Advertising channel PDU contains two parts, header and payload. The header consists of 6 fields. The PDU type field indicates the PDU type. The table is the definition of all PDU types. RFU is equivalent to reserved for future use. The CH-select, TX address, and RX address fields contain information specific to the PDU type defined for each advertising physical channel PDU separately. If the CH-select, TX address, or RX address fields are not defined as used in a given PDU, then they should be considered reserved for future use. The length field indicates the length of the payload in octets. The valid range of the length field should be 1 to 255 octets. The payload consists of ADVA and ADV data fields. The ADVA field should contain the advertiser's public or random device address as indicated by TX address. If TX address is 0, the advertiser's address is public. If TX address is 1, the advertiser's address is random. The ADV data field, if not empty, should contain advertising data from the advertiser's host. This is the connection request packet sent by the central. Only the content of the payload is changed. The payload consists of init-A, ADVA, and area data fields. If TX address is 0, the initiator's device address in the init-A field is public. If TX address is 1, the initiator's device address in the init-A field is random. If RX address is 0, the advertiser's device address in the ADVA field is public. If RX address is 1, the advertiser's device address in the ADVA field is random. The area data consists of 10 fields. The AA field should contain the SAL connection's access address determined by the link layer. The CRC init field should contain the initialization value for the CRC calculation for the SAL connection. It should be a random value generated by the link layer. The window size, window offset, interval, latency, and timeout fields has been explained before. The CHM field should contain the channel map indicating used and unused data channels. Every channel is represented with a bit positioned. The LSB represents data channel index 0, and the bit in the position 36 represents data channel index 36. A bit value of 0 indicates that the channel is unused. A bit value of 1 indicates that the channel is used. The hop field should be set to indicate the hop increment used in the data channel selection algorithm. It should have a random value in the range 5 to 16. The SCA field should be set to indicate the central SCA used to determine the central's worst-case sleep clock accuracy. The clock accuracy setting in the central routine is 50 ppm, so the value of SCA here is 5. This is the version indication packet sent by central and peripheral. The composition of the PDU has changed. The data physical channel PDU has a 16 or 24-bit header, a variable size payload, and an optional MIC field. The MIC field should not be included in an unencrypted SAL connection. The header consists of 8 fields. If the area ID field is 0 or 1, the data physical channel PDU payload contains an area data PDU. If the area ID field is 3, then the data physical channel PDU payload contains an area control PDU. The full name of NESN is next expected sequence number. The full name of SN is sequence number. These two fields are related to BLE's retransmission mechanism. The MD field is used to indicate whether the device has more data to send in the current connection event. If either or both of the devices has set the MD bit, the central may continue the connection event by sending another packet, and the peripheral should listen after sending its packet. The CP field indicates whether the data physical channel PDU header has a CTE info field, and therefore whether the data physical channel packet has a constant time extension. The length field indicates the length of the payload and MIC if included. The length field has the range 0 to 255 octets. The payload should be less than or equal to 251 octets in length. The CTE info field is present if indicated in the CP field. The CTE info field indicates the type and length of the constant time extension. The payload consists of opcode and control data fields. The opcode field identifies different types of area control PDU. The table is a definition of all area control PDU types. The control data consists of 3 fields. Version field should contain the version of the Bluetooth link layer specification supported by the controller. OXOC means support BLE 5.3 specification. Company identifier field should contain the company identifier of the manufacturer of the Bluetooth controller. OX07D7 is the identifier of WCH. Subversion field should contain a unique value for each implementation or reversion of an implementation of the Bluetooth controller. This is the area feature request packet sent by the central and the area feature response packet sent by the peripheral. The combination of the area control PDU has changed. In an area feature request, feature set should contain the set of features supported by the central's link layer. In area feature response, byte 0 of feature set should contain a set of features supported by the link layers of both the central and the peripheral. Bytes 1 to 7 of feature set should contain a set of features supported by the link layer that transmits this PDU. A bit set to 0 indicates that the link layer feature is not supported in this controller. A bit set to 1 indicates that the link layer feature is supported in this controller. This is the area length request packet sent by the central and the area length response packet sent by the peripheral. The combination of the area control PDU has changed. Max RX octets is the maximum number of octets in the payload that the local device is able to receive from the remote device. The max RX octets field should have a value not less than 27 octets. Max RX time is the maximum number of microseconds that the local device can take to receive a packet from the remote device. The max RX time field should have a value no less than 328 microseconds. Max TX octets is the maximum number of octets in the payload that the local device will send to the remote device. The max TX octets field should have a value no less than 27 octets. Max TX time is the maximum number of microseconds that the local device will take to transmit a packet to the remote device. The max TX time field should have a value no less than 328 microseconds. This is the area channel reporting indication packet sent by the central. The combination of the area control PDU has changed. Enable should be set to indicate whether channel classification reporting needs to be enabled or disabled. Mean spacing should be set to indicate, in units of 200 milliseconds, the minimum amount of time from the last area channel status indication PDU that was sent before the next area channel status indication PDU may be sent. The value should be between 5 and 150. Max delay should be set to indicate, in units of 200 milliseconds, the maximum amount of time between the change in the channel classification being detected by the peripheral and its generation of an area channel status indication PDU. The value should be between 5 and 150. Max delay should be greater than or equal to mean spacing. This is the area connection parameter request packet sent by the central and the area connection parameter response packet sent by the peripheral. The combination of the area control PDU has changed. The interval mean, interval max, latency, and timeout fields have been explained before. The preferred periodicity field should be set to indicate a value that the connection interval is preferred to be a multiple of. Preferred periodicity is in units of 1.25 milliseconds. If the preferred periodicity is set to 100, it implies that the connection interval is preferred to be any multiple of 125 milliseconds. The value of 0 means no preference. The preferred periodicity should be less than or equal to interval max. The reference connection event count field should be set to indicate the value of the connection event counter relative to which all the valid offset 0 to offset 5 fields have been calculated. The offset 0 to offset 5 fields should be set to indicate the possible values of the position of the anchor points of the LE connection with the updated connection parameters relative to the reference connection event count. This is the ALL connection update indication packet sent by the central. The combination of the ALL control PDU has changed. The win size, win offset, interval, latency, and timeout fields have been explained before. The instant field should be used to indicate the connection event count when updated parameters should be applied. This is known as the instant. When the payload of data channel PDU becomes ALL data PDU, the combination of the payload will change. An ALL data PDU is a data channel PDU that is used to send L2CAP data. L2CAP PDU has PDU length, channel ID, and information payload fields. The PDU length equals the information payload size. The channel ID identifies the destination channel endpoint of the packet. The information payload contains the payload received from the uplayer protocol or delivered to the uplayer protocol. The payload size should not be greater than the peer device's MTU for the channel. Let's talk about several types of packets when the information payload is attribute PDU. The attribute PDU is composed of 3 fields. The attribute opcode field identifies different types of attribute PDU. The table is a definition of all attribute PDU types. Attribute parameters field are determined by the type of attribute opcodes. Authentication signature field is optional. Attribute opcode contains an authentication signature flag. If the authentication signature flag is set to 1, the authentication signature value should be appended to the end of the attribute PDU. If the authentication signature flag is set to 0, the authentication signature value should not be appended. The ATT error response PDU is used to state that a given request cannot be performed and to provide the reason. The request opcode in error parameter should be set to the attribute opcode of the request that generated this error. The attribute handle in error parameter should be set to the attribute handle in the original request that generated this error. If there was no attribute handle in the original request, or if the request is not supported, then the value OX0000 should be used for this field. The error code parameter should be set to a value from the table. The ATT find by type value request PDU is used to obtain the handles of attributes that have a 16-bit UUID attribute type and attribute value. Only attributes with attribute handles between and including the starting handle parameter and the ending handle parameter that match the requested attribute type and the attribute value that have sufficient permissions to allow reading will be returned. If one or more handles will be returned, an ATT find by type value response PDU should be sent. The handles information list field is a list of one or more handle information. If no attributes will be returned, an ATT error response PDU should be sent by the server with the error code parameter set to attribute not found. The ATT read by type request PDU is used to obtain the value of attributes where the attribute type is none but the handle is not none. Only the attributes with attribute handles between and including the starting handle and the ending handle with the attribute type that is the same as the attribute type given will be returned. Only attributes that can be read should be returned in an ATT read by type response PDU. The ATT read by type response PDU should contain complete handle value pairs. Such pairs should not be split across response packets. The handle value pairs should be returned sequentially based on the attribute handle. The length parameter should be set to the size of one attribute handle value pair. The ATT write request PDU is used to request the server to write the value of an attribute and acknowledge that this has been achieved in an ATT write response PDU. The attribute handle should be set to a valid handle. The attribute value should be set to the new value of the attribute. If the attribute value has a variable length, then the attribute value should be truncated or lengthened to match the length of the attribute value parameter. The ATT write response PDU is sent in reply to a valid ATT write request PDU and acknowledges that the attribute has been successfully written. The ATT read request PDU is used to request the server to read the value of an attribute and return its value in an ATT read response PDU. The server should respond with an ATT read response PDU if the handle is valid and the attribute has sufficient permissions to allow reading. The attribute value should be set to the value of the attribute identified by the attribute handle in the request. If the attribute value is longer than ATT MTU-1, then the first ATT MTU-1 octets should be included in this response. A server can send a notification of an attribute's value at any time. The attribute handle should be set to a valid handle. The attribute value should be set to the current value of attribute identified by the attribute handle. If the attribute value is longer than ATT MTU-3 octets, then only the first ATT MTU-3 octets of this attribute's value can be sent in a notification. If the attribute handle or the attribute value is invalid, then this notification should be ignored upon reception. The packages explained above are captured during the connection between the central and the peripheral. There are many other packages waiting for you to learn. The content of this section ends here. Thank you everyone.